Hey, welcome to another episode of DevHub Live. We have an extra bonus episode today. Let me get rid of this banner in front of my face. Here we go. This is a great one if you're building on chain abstraction, chain signatures. We have Matt from Proximity here today to kind of go through some different stuff. He's been working on all kinds of really cool tech around this, and I think it's going to be a great session. If you haven't signed up already, at the bottom we have the link for the Redacted Hackathon set up there, so you can get started there. You still have until October, end of October, to build. There's multiple different bounties you can go in and do. So there's a lot of great opportunities here. But I want to maximize this time. You can ask questions if you're watching here live. You can ask questions. We will try to address those as best as possible. But I want to make sure that we have enough time to get through some different things here and have Matt really introduce us to some of the really cool things that can actually happen on here. So without any further ado, let me bring up Matt Lockyer to the stage. Hey, Matt. Thanks for joining us.
Hey, Joe. Yeah, good to see you. It's been a while. Yeah, it's really great to be here. And coming in and out of focus, but yeah, I have a lot to share about chain signatures. It's gonna be a little bit kind of anticlimactical. We're not going to be doing anything live right now. The chain signatures team working tirelessly. They're upgrading a few things right now. So the test net and the main net are just a little bit in flux. But I have a video that I pre-recorded about a month ago based on something I call my chain sig script, which is basically like a multi-chain. You can execute transactions on any chain. And then I'm going to walk through that and explain kind of how that works. But I'm also going to go through the more detailed example or like the more advanced example. And that example is really cool. Basically, what we do is we use chain signatures to deploy an NFT contract on Ethereum. And then we call through a near contract. We call the chain signatures contract, and then we basically mint an NFT. And the reason why you'd want to use chain signatures through a near contract is because this allows you to basically build like a protocol. And then we'll go into like a discussion, like maybe you and me, we can start that off about different applications of chain signatures and kind of how to build these multi-chain protocols. Regardless, it's a great technology. It's something that's got me really fired up about Near lately. And there's tons of applications, pretty much endless applications.
No, that's awesome, and I'm excited that you brought up that part, because one of the questions that I've heard come up a few times now is the concept of actually like using chain signatures on Near, not just kind of going outward. So I think that's a cool part to kind of touch on as well. Um, let's start however you want to jump into this.
Sure. Yeah, I'm going to go ahead. I'm just going to share my screen.
Sure.
Just one sec. There we go. Cool. Yeah, we got multiple windows here. First, I just want to mention that, and I'll come back to this in a bit, but Proximity is putting up a lot of bounties for the Redacted Hackathon. So this is all to do with chain abstraction, chain signatures. The requirements is, of course, interoperability. It's all about chain abstraction. So you got to use Near plus at least one other blockchain. There's going to be, basically some marks for user experience and security and innovation. So showing some creative uses of Near's chain abstraction. And then here's the evaluation criteria, but we can come back to this later if we have time. The one big thing to notice is that there's $35,000 in prizes. So definitely, if you're in the Redacted Hackathon, something to think about. DeFi and Bitcoin are basically like the real big things that Proximity is looking at. So you can do a lot with chain signatures, including leveraging non-smart contract chains like Bitcoin, using chain signatures. So you can build interesting protocols. You can do lots with DeFi. So just definitely something to check out.
Awesome.
So do you just want to jump in? So basically, I'm just going to chat a little bit about this repo that I put together several months ago when chain signatures was just kind of just a sort of a beginning technology on Near. So it has been around for quite a while, and this is just called the chainsig script. So it's under github.com near-examples/chainsig-script. So basically, just a general overview of the repo, and there is an accompanying workshop video off to the side, which I can kind of jump into in a sec. It's actually got some transactions running, so we can like see how this works. But just to jump into the overview, it's basically just a command line, and I just want to go through the source here. You can see there's multiple different chains here. We actually had a team from Cosmos basically make a Cosmos contribution. So I didn't even do that. They just recently made a PR. So thanks to the Arai team for doing that. And then other chains that I implemented a while ago were like obviously Ethereum, Bitcoin, Dogecoin, and even XRP. So because chain signatures just produces an ECDSA signature, we were able to actually execute transactions on all those other chains. So 5 different chains are basically encompassed in this repo. But let's take a step back and really think about like what is chain signatures in general. Let's do like the basics. So the chain signatures protocol in Near basically allows you to just do a simple Near kind of function call to the chain signatures contract and basically get back an ECDSA signature for any hash or like payload that you would want to sign. So we all know, like on different blockchains, Ethereum, Bitcoin, what have you, all the transactions basically get hashed at some point, whether it's a SHA-256 or whether it's like a Kekak hash on Ethereum. All the transaction details get hashed down into basically 32 bytes. So how do you sign those 32 bytes? Well, that's where the chain signatures team came in, and they basically created this protocol that allows us to use a multi-party sort of set of nodes to produce a secure signature for any hash. Now, how do we actually get a hash? Well, we basically have to call the Near chain signatures contract. Now, we're making a signature for a hash, but another question comes up. What's the account that we're actually signing for or from, right? Like typically if we make a signature, it's signed by some private key, and that private key has an accompanying public key. And what we know about public private key pairs on chains like Bitcoin and Ethereum is that they also the public keys also represent the addresses in. There's a bit of kind of code and massaging to get to the address, but basically the public key and the address are kind of like a one-to-one. There's a one-to-one correspondence there. So how do we get a public key for the chain signatures account that we're going to get the signature for the hash from? Well, I like to kind of keep this really, really simple. So we call it a derived account on chain signatures. So for example, if we wanted a public key for an Ethereum account, we would basically be calling the Near chain signatures account from this Near account ID. Let's say it's, mat.near. We would add a path variable. So you could think of this like a hardware offset, like on a ledger. We have like, different hardware offsets off of our device to get different accounts. So you can pass in anything you want. The path variable is just a string. So typically, if you're looking for an Ethereum derived account, you'd pass in like Ethereum, 1, and then you would get basically a derived account. So the next time you call sign on the chain signatures contract and you pass it the hash that you want to sign, or what we call sometimes the payload of 32 bytes, you would also pass in the path variable, and then the signature you would get would correspond to that derived account. And if you took the hash and the signature and you ran it through a typical, what they call like an EC recover or ECDSA recovery from a signed payload, you would basically get the derived account's public key. So so that's basically kind of like the basics of chain signatures. All the chain signatures protocol does, just want to keep it super simple for people who are hacking on this, all the chain signatures protocol does really is expose the sign method. You pass in a hash and a path, and you basically get a signature for your derived account. Now, a lot of people kind of are thinking, okay, well, how do I actually know what my derived account is going to be ahead of time, right? Like, how do I actually generate that? Well, in this repo and in another example repo I'll talk about in a sec, we have a file called KDF. There's a lot of there's a lot of code going on here, but basically I've tried to simplify it as much as possible by boiling everything down to a generate address method here, or function where you can just say, okay, I've got there's a few kind of extra bits. Like I've got the public key of the chain signatures contract. That's just kind of a requirement. It's really easy to get that. I've got the account ID of the near account I'm calling from. So that was the account ID we saw before, the near account ID. I've got the path, and then you just tell it which chain you want. So you just say, I want an Ethereum address. And this script will go ahead and it'll just generate an Ethereum address for you. And then at the end, it'll just return that information. It'll return the address and actually the public key as well. So basically, it was a long-winded way of saying, how do I get my derived account kind of offline, or how do I actually get a derived account before I call the chain signature sign method with my hash? Like, and the reason you'd want to do that is you'd want to fund that derived account, or you'd want to know which derived account is going to actually be called on to execute that final signed transaction. So the KDF script is what you can do. You can call that offline. You can generate as many derived accounts as you want, and then it really comes down to what your application is, what your protocol is, and what you're planning to do with those derived accounts. So so the KDF script is basically just like a deterministic way to generate these derived accounts. So
I want to just clarify something for people.
Yeah.
When you say Ethereum, you're meaning all EVMs. You're not differentiating between different L2s, or are you?
No, yeah, that's a great point. I'm trying to actually go back through these code examples and rename Ethereum to EVM and stuff, because it basically is any EVM chain. You bring up a really interesting point though. For derived accounts, you probably, if you're going to mainnet with this, you'd probably want to make sure that one derived account on your kind of multi-chain protocol would not create the same EVM address for multiple chains, because there could be some issues where you're on kind of two different L2s with the same address. So that's where this path variable might come in handy. Like, you might want to basically, let's say you wanted to restrict a user to just the Ethereum mainnet, you might want to do, Ethereum underscore mainnet, comma 1, comma 2, comma 3 for different derived accounts for mainnet. It's just an idea. It's probably kind of prudent to do something like that, but just great brainstorming there. But yeah, the derived accounts could actually be used on any EVM chain. And also the derived accounts, remember, if we go back to this KDF script, what we're really looking at is, like, we can get Ethereum. I have BTC for BTC mainnet, and then I have Bitcoin for Bitcoin testnet, Dogecoin, XRP, Cosmos is here. And really what we're getting is we're just getting entropy, and we're basically generating, you know, sometimes the addresses have different kind of configurations, how they're generated from the public key, but we're really just getting ECDSA key pairs at the end of the day. And so it's like whatever we pass into this path variable will create an ECDSA key pair, and then we can use it wherever we want, wherever you know, wherever a chain uses ECDSA. And by the way, ED25519 signatures will also be coming to chain signatures soon. So there'll be an actual ability to not just specify your path, but specify like your key version, and then you'll be able to generate ED25519 signatures for chains, you know, like Solana and other chains that use those signatures. Does that kind of answer the question?
Yeah, I think so. Yeah, it's, you know, I want to make sure that people truly understand like how powerful this stuff is, and like it's really not limiting, especially as, you know, these next version comes out, and you can now go to pretty much once you add in the next key. Now we're talking about, right, Solana and other chains. Like pretty much everything's encompassed, and so now it's truly an open door to build across everything that you can think of in crypto.
Yeah, exactly. It's a very low level protocol, but because, you know, because we kind of cook it up with names like chain abstraction and chain signatures and derived accounts and stuff, it seems more complicated than it is, but it's very simple. You basically just need two components. You need to basically use some sort of key derivation script, which is the one that I showed earlier, as part of this chainsig script repo. You basically need that to generate these derived accounts offline. And really, when you're generating a derived account, there's no magic to whether it's Ethereum, EVM, Bitcoin, Dogecoin, whatever. It's basically just an ECDSA public key. And then the account is basically, you know, like generated off of that public key. Now you can generate as many as you want because of this path variable and the corresponding the caller near account ID. And now this is, if you're in the near world, you know, it makes sense to mention that this is always going to be the predecessor caller to the chain signatures contract combined with this path variable. I want to touch on that later, because sometimes we're not just calling the chain signatures account from a near account, like directly from a client account. Sometimes we're calling it from a near smart contract, which will change the entire derived accounts that get created. So I'll come back to that point later. But it's basically just those derived accounts. How do we derive them? We use the script. You can add the script to your app, or, you know, if you're running it on a back end, you know, it can just spit out as many derived accounts as you want. And then it comes down to getting signatures. So just calling that sign method, and basically, let's just cruise down here to calling the MPC sign method. So the near account will call the sign method, and it specifies the path, which is what we saw from the KDF stuff before, the payload, and the key version. For now, the key version is just 0. But in the future, like I mentioned, there'll be different key versions like ED25019 and other things. So so that's really all there is to it. The near account will call the MPC contract, and then it'll return a signature for the derived account. So there's really just like those two parts. You know, you want to create an account on a different chain, right? And then basically you want to sign something for it. That's all there is to it. Did you want to kind of recap anything there, Joe?
No, I think this is, yeah, I think we're on a good track here.
Cool. Yeah, and I just wanted to mention, like, just going back to this example here, there's a bunch of pre-built accounts that can basically kind of help simplify a lot of things. Like if you just type yarn start and then just -EA, for example, you'll just get an Ethereum address. A little typo there, but you'll basically get an Ethereum address, and that'll be based on your path variable that you specify in your environment in your environment variables. I included like an environment variable sample here, and here's my MPC path. So basically you could change, if I change that Ethereum comma 1 to Ethereum comma 2, for example, I'd get a different derived account.
Nice.
So you can just run yarn start EA. You can run yarn start ETX, which would prompt you to send ETH. And then there's a few more configurations, like you can set the amount and the two. And the reason why it's just like these basic commands is because it tried to kind of make it kind of like multi-chain accessible. So you don't just have to send Ethereum. You could, for example, send Bitcoin from the derived account. Now, it does require you to kind of pre-fund the derived account, which is why the first step is usually figuring out what your derived account address is. You would put some funds in there, and then if you wanted to use chain signature to send funds from there, you could use this. Let's say it's Bitcoin. You could use this yarn start -btx command, and then you could specify an amount or a two. There are default amounts and default kind of destination addresses built in. They're usually going to me, thanks, but it's all testnet. But yeah, that's just simplified commands and stuff. And this was just this goes all the way back to me, like in the very beginning, kind of just creating some basic tooling to kind of see everything we could do with chain signatures and just kind of push the limits. And you could think of it kind of like it's a bit of a script kind of command line tool, but it's also a bit for kind of debugging and testing the chain signatures functionality as well. Like just what can we do? Can we deploy an EVM contract? Well, sure. We can use these commands to do it. Can we make Ethereum contract calls through chain signatures? Sure, we can, right? So I just wrapped up some of that functionality and created that there. The EVM contract deployment and interactions, that's actually a cool place to dig in if you wanna take a look at that at a later time. But yeah, I want to go back to this sign method call, because it's really just like it's the second component of chain signatures. And so to do this sign call from your near account or from your near contract, you're basically just going to pass in this request argument. So it is a single object kind of called request or struct in Rust. And then it's basically just the payload, which I mentioned was 32 bytes. The path variable, which is a string. So for example, Ethereum comma 1 or Bitcoin comma 1. And then the key version, which right now is just 0. And then basically that so the MPC nodes will spring into action, and then they'll basically they each produce part of your signature, and then basically your signature is kind of composed and sent back to you. One thing that I think people might ask about is, sorry, I don't want to jump around too much, but one thing people might ask about these derived accounts is that, sure, you can get a derived account, but sometimes people get hung up on the fact that, yes, this is a public key, but people think, well, where's the private key? It's a public key. There's got to be a private public key pair, right? And that is a very interesting question. But in fact, there is no private key for any of these derived accounts. So there's, if you kind of mess up with a derived account, or you fund it or something, or you forget, let's say you forget your path variable or whatever, for whatever reason, there's no seed phrase or private key that was ever generated for this account. So, and that is kind of built in by design. And that's so that when you're doing these chain signatures, when you're building these chain signature protocols with these derived accounts, it's so that basically like there's no leakage of like, another way to execute these transactions. So remember, like the only way to execute these transactions, the only way to call sign is from the near account with the right path variable for that derived account. And that's the only way to generate that signature. So there's never, when you derive the accounts, there's never going to be a private key. And also,
so if I lose, so if I do have, I forget my path variable for whatever reason, I lose it. Am I locked out of that? Well, those funds are lost.
yeah, if you lose control over the near account they're calling from, or if you just mess up, and let's say your path variables were randomly generated, like it was near account ID plus some sort of seed phrase, that
Yep.
was just the way you designed your protocol. Let's say you misplaced that seed phrase, then yeah, the control over the derived account is gone, basically, right?
Mm-hmm.
And it is a security thing. Like if you think about it, like you don't want any, like obviously you don't want any near account to be able to say, hey, Ethereum comma one, and then access Joe's funds in his derived account on, let's say,
Right.
Optimism or something, right?
Right.
Like you don't want anyone else to be able to do that. But also, this is a really interesting point, is how these derived accounts are made. Is that, I mentioned that the chain signatures is a multi-party computation protocol. So the chain signatures nodes themselves, they also produce this public key, which is part of this derived account calculation. And we typically call it the MPC public key, or the near chain signatures contract public key. Now, that public key is the shared public key from all the nodes. And then you might be asking, well, again, there's a public key. Where is the private key? There is none. And that's the design of basically an MPC system, is that you've got all these nodes and they produce some shared entropy, but none of the nodes would ever be able to compose the actual private key, because if they could, it'd be as if they had a master key to everything, right?
Right.
So that's just kind of that's just the general kind of like high level abstract, like how does it all work kind of thing. I do want to get into this stuff, because this is the meat and potatoes, and about how to build kind of applications and protocols. So if you dive into this chainsig script example later, and you kind of dive into the code and stuff, you're going to come across this Ethereum EVM contract example. Now, what we're trying to do here is we're basically going to get the near account to basically call the MPC contract and get a signature for a derived account. We're going to take that derived EVM account, we're going to deploy an NFT contract to it. Now there's an NFT contract deployed to this Ethereum derived address. Now remember, the Ethereum derived address, it is an Ethereum account, it exists, but there's no private key, there's no way to import it into MetaMask or whatever. The only way to control this Ethereum account is through a call to the near MPC or chain signatures contract from the originating near account. So how do we actually mint an NFT on that Ethereum, that NFT contract we just deployed on Ethereum? Well, we have to call again from the same near account to the MPC contract, get a signature for the mint transaction. And then what we do is, for the derived EVM account, we take that signature, combine it with the mint transaction that we composed and hashed when we passed the payload to the MPC contract, and then we broadcast it to, for example, Sepolia testnet, and an NFT will be minted. So what's really cool here is that we basically can deploy, we can deploy an Ethereum account, put a little bit of funds in it, make it an NFT contract, and then we can just start minting NFTs from that Ethereum account into other EVM accounts as well. Like we can say that the owner of the newly minted NFT should be this address or that address. And we can do this all from basically from near calls, right? So what that means is basically the application logic for distributing these NFTs on on an EVM chain. So, for example, it could be on Ethereum, it could be on Optimism, it could be on Arbitrum. It doesn't matter. But the logic for distributing these NFTs comes from basically a near account or a near smart contract, and that's the last part I wanted to get to, which is you can actually call the near chain signatures contract from your own near contract. So this is going to involve, and we'll dive into the code after this, because I think some people will probably want to get into like the actual cross contract call and kind of take a look at that. But
Yep.
this is really where chain signatures kind of shines, is that we can actually create a custom near contract, and then we can call the near chain signatures contract from that contract, and we can get back the signature and then return that to the client. Now, why would we want to call? Why wouldn't we just want to call the chain signatures contract directly from a near account, like in this example? Well, you know, a near account kind of, or what they would call on an EVM chain, like an externally owned account. It's kind of basic, right? There's no
Right.
logic, there's no rules to it, there's no code, right? But if we can call the MPC contract from our own custom contract, we can enforce a lot of different kind of rules and logic. So in the example that I've made, I actually require, we'll just skip down to step 2 here. I require that if you're calling the near custom contract from any near account, and I specify that because you can call the custom contract as itself, you know, like a near contract owner could call itself, right, in its method. But basically, I've restricted this near custom contract, and I'll walk through the logic of how I did that later in just like 2 minutes. Any near account that calls this custom contract and wants to mint an NFT on the EVM account to any other EVM address, I require that they have to pay one near. So there's actually like a bit of logic there. Basically says, okay, if you want to mint an NFT over on Ethereum, I'm going to actually ask you to pay one near token to do that. And then the near custom contract will call the MPC contract and get that signature for the mint transaction. Now it's going to return that. It's going to return that all the way through to this calling near account, which will combine it with the derived EVM account where we know the NFT contract is residing. And then the mint transaction can be broadcasted and executed, and the NFT can actually be minted to the user. So let's think about this for a second, right? Like, we're creating an application that basically requires near users to kind of roll up to the gate, you know, pay one near for entry to get that EVM NFT minted, right? So, and it doesn't have to be one near, you know, I mean, the sky's the limit. You could do whatever you want. Now, we're describing an example where near accounts have to kind of come up with the funds to pay for this NFT. But there is another interesting way to do this. And I personally have not created an example like this, but it's the way that a lot of people are creating their sort of like their DeFi examples or their their multi-chain examples by basically sidestepping. Well, that's not the right word. We're trying to come up with a way where the currency to mint, let's say the currency to mint an NFT doesn't always have to be near. It doesn't have to be near accounts paying one near. So how would you kind of change this example? Well, in the near custom contract, what we could be looking for is generating a derived account where we're looking for an input or a payment into that derived account, right? So what a relayer or let's assume the user has no idea or no knowledge of near. A relayer or someone that's looking at that derived account that the custom contract made, let's say that's just a deposit. It's a deposit account for making a payment, right? So let's say it's like an Ethereum account, and the requirement was to actually pay 0.01 ETH or whatever to mint an NFT. So what we could do is we could actually watch a derived Ethereum address, and then once the payment is made, we could transfer that payment out of that Ethereum account and into basically like a holding account for that protocol, and we would know that payment's been made, and then we could call the MPC contract and mint the NFT. So you see how there's kind of like different ways to flip it. Like we
Right.
don't have to use the derived account. The derived account doesn't always have to be used as like the last step. It could be used like as a funding step as well. So that's how a lot of people are kind of thinking about chain signatures. They're saying, hey, fund this derived address
Yep.
that my smart contract has control over. And if you fund that address, I will credit you this token or this other thing on this other chain. So you can kind of see how it starts the possibilities start to get really wild, right?
Yeah.
Now, in order to do some of that stuff safely and securely, you need to have like kind of like a prover on that other chain, or some relayers or something to set up to basically make sure that the transactions are going through. The funding was definitely completed on the other chain before you would kind of spring your custom contract into action. Does that
Right.
make sense?
Yeah. So is that logic that's handling two parts of this? One, that logic is handling off chain or both? Or either or, I guess.
Well, you would do basically your protocol would create this derived account. Let's say you were funding it with Bitcoin or Ethereum or whatever, and then you would tell you'd tell the user send X amount to this address. Now the protocol itself controls that address through chain signatures, right? So once the funds are deposited into that account,
Nice.
obviously the user can't move them,
Yep.
but it's controlled by chain signatures. So it's controlled by the smart contract logic of the contract that created the derived address, right?
Mm-hmm.
So you're basically kind of telling people it. You could think of it kind of like it's a bit of it's like a lockup, right? Like it's sort
Right.
of like send funds to this lockup, and then if you want to go ahead and mint the NFT, or if you want to go ahead and leverage those funds in a DeFi protocol or something, you can go ahead and do that with this synthetic token that I'm going to credit you because you deposited funds into that chain signatures derived account. Does that make sense?
Got it. Yeah. So then from there, is this essentially, if you're taking this approach, so on Near, we have the concept of meta transactions. Is this kind of like a chain abstracted way of thinking of like meta transactions? Like does it lead to that? I'm sorry, let me phrase it. Does it lead it to that path of having something like that where I can essentially take on that cost for my user?
Um, Yeah, that's an interesting point. So it doesn't have anything directly to do with meta transactions. However, there are ways to basically combine meta transactions with that kind of a design. Like I mentioned that, the user coming from, let's just say, chain X,
Yep.
they have no knowledge of Near, and so they're just going to deposit into a derived account on chain X. And then after some amount of time, the protocol is going to basically credit them, some token or some gas or something
Yep.
to basically be able to sort of continue on with the protocol on Near as the application logic. But if this was a multi-chain, like a chain X to chain Y kind of scenario, and we were using chain signatures, deposited into a derived account on chain X, then we're going to credit you some funds on chain Y. I mean, like you can see right away where the sky's the limit. Now, how do we pay for all those Near transactions to basically execute the sign calls to the MPC contract? That's a great question. And meta transactions is one way to accomplish that. And then the other way is sort of kind of an older school method, is like custom relayers and things like that, right? For
Sure.
that particular protocol.
Yeah. I think, and what I want to highlight to viewers, if you're doing the hackathon, So one of the things we talked about with David and the other one about chain abstraction was the concept of like you could pair, Near's account abstraction with this, and now you have that easy onboarding for users. Now we can also take it a step further, combine a concept like a meta transaction, and start to kind of fund parts of this. And now, from a user experience, you could build a really interesting product that onboards somebody with pretty much zero friction, but now you're able to leverage multiple chains in your product. And then at some point, maybe, funding maybe comes from someplace else, whatever else, but you have that ability to leverage those near already made infrastructure pieces to this protocol as well.
Yeah, no, exactly. And I'm going to touch on something else in just a moment. I just want to I'll quickly buzz through this contract. So this is the contract that I mentioned is doing the cross contract call to the chain signatures contract. Right away, you can see that there's a sign request. And again, why are we calling the chain signatures contract from a custom near contract? It's because we want to build in some sort of application logic, even the most basic logic, which is some cost. Okay, we're going to require that this costs one near token. We're just going to build in some logic, and then we're going to call the chain signatures contract. So we're not just going to let anyone basically get a signature to mint an NFT on an Ethereum contract, for example. We're not just going to let any near account do that. We're going to make them all call through our near smart contract, and that smart contract is going to require them to basically have paid one near token. So I want to go through this sign method. So this is a custom sign method specific to this protocol. And basically it takes in, it doesn't take in the full hash of the Ethereum transaction. It takes in what's called the RLP encoded payload. Now the reason it takes in this payload is because as a sort of a very, very, very basic protocol, we want to inspect something about this payload. And what we want to inspect is if the user, the near account that is calling the sign method is using one of the public RLP encoded method names. Now, I know this gets a little bit kind of cryptic, but basically this is just the hash of the mint function call to an Ethereum NFT contract or an EVM NFT contract. So this is just really, when you make a mint function call, this is just the mint method. So the reason why I have that is because what I'm searching for in the RLP payload is that the RLP payload includes that mint call. So now I know that this is it's a public account, and they're trying to call one of the public methods. So I basically said, okay, this is a public method call. If it's not a public method call, I require that this is the owner of the contract calling, but that's not really that important. But basically, so we've passed this public check. Yes, they're trying to call the mint method of the EVM contract. Okay, so now this Ethereum account, what do? We actually hash the RLP encoded payload. So in Ethereum, it's a Keccak 256 hash. So we basically decode the hex RLP payload and we hash it. So we decode that into bytes, and then we hash those bytes. And what we get is we get the payload that we're going to call the MPC contract with. Now, the last thing to check, and actually we probably should have done it before we spent gas hashing this. So these are kind of reversed. It's a little bit of mistake on my part, but this should be after this. But what we are going to check is we're going to check the attached deposit, and we're going to make sure that the deposit is greater than or equal to the cost. And I just put a funny, pay the piper here. Basically, if you're not the owner of the contract, I'm requiring that you pay me one near token in order to continue on and to basically call the MPC contract. So again, it's very, very simple. It's a bit I wouldn't say it's contrived. It's pay one near token and mint an NFT on an Ethereum testnet, right? Or it's pay one near testnet token. But basically, it shows how to kind of like think about these cross-contract calls, where you would kind of put in your application logic, maybe how you would put it in, and really what you're going to want to do is you're going to want to inspect the payloads that the user is going to eventually kind of get hashed and signed, right? So
Yep.
Some level of transaction construction would need to kind of happen in the Ethereum, in the near contract in order to kind of construct that EVM transaction and eventually hash it so that a signature can be created. This is a perfect time to actually jump into another example that we've been working on. This is still a bit in development, but it's something I can kind of go over very briefly. So this is something I call trade signatures, and it is a bit of a joke, but it's basically it's trading one signature for another. And now, why would we want to do this? Well, Joe, you brought up usability and you brought up this frictionless onboarding.
Mm-hmm.
So really what we'd love to do sometimes is we'd love to have the user basically show up with their MetaMask or their Bitcoin wallet or whatever wallet from whatever chain. And we'd love them to be able to sign a transaction payload and then have that executed by chain signatures, and basically we're gonna have them sign a payload in their wallet, and then we're gonna take that signature, we're gonna verify that they actually signed that payload to get that thing done on that other chain, and then through chain signatures we're gonna execute that. So let me just show you the contract here really quick. I'll just jump into it. So there's a method here called trade signature. And basically what we pass in is we pass in an owner, and this could be a public key for Bitcoin or an address for an EVM chain. We get a message and a signature. And the message is the payload of the transaction that was signed. So this payload is usually destined for, we're only working with 3 chains here for the destination chain: Bitcoin, EVM, and Near. So the payload is basically like, it's a partially signed Bitcoin transaction, or it's a very basic Ethereum transaction, 2 value args, things like that, or it's a Near transaction, and it's like an unsigned Near transaction. So when this message payload comes in, it's basically stringified JSON of the entire transaction, and the user has already signed this in their wallet. For example, like in the OKX wallet, you can sign for Bitcoin or for an EVM chain. Right. And then what we do is we also pass in the signature. So using these 3 components, the first step is that we would, right now the source chain is only Bitcoin and EVM, but I'll be adding Near soon. But basically, we will require that the owner, the message, and the signature all kind of, let's say, just to simplify it, add up, right? So basically, we should be able to recover this owner variable. In Bitcoin, it's going to be a public key from the message and the signature. In the Ethereum case, it's going to be the address, but same thing, public key to address is deterministic. Yep. So what we're going to do is we're going to require that the owner is a Bitcoin owner or an EVM owner, depending on what your source chain is. And then we're going to pass in the message, and we're going to return basically a signature for that destination chain. So just to jump into like what one of these looks like is, we'll go back into, let's just look at Bitcoin owner. So here's the require method. So the recovered PK from all of this, signed Bitcoin message parsing and stuff, that's going to eventually, basically recover the public key. And then we're going to make sure that that recovered PK equals the PK that we passed in. So that owner is the public key. If we signed an EVM, let's say we signed an EVM payload with our Bitcoin wallet, then the next thing to do is to actually get an EVM transaction from that payload. So this is where we're using actually a library that Proximity is developing called the Omni library. And this is a transaction builder. So basically you can see on this get transaction method, we just have to call EVM transaction from JSON and then pass in a JSON payload. And the Omni library is actually going to parse it into an EVM transaction object for us. And then we can actually just simply call build for signing. And then we can do, and that will create the RLP encoded EVM transaction. And then we can just hash it. And that gives us the payload. And then in this particular Rust contract, I basically put the chain signatures call under ECDSA here, just to signify that one signature type. And we just call ECDSA get sig, and that's right here. And just like the previous example where I was doing a cross-contract call, you can see that there's a cross-contract call to the MPC contract. So this is where we're going to return, we're going to call, sign, and return the signature. So it's pretty cool stuff. This near trade signatures repo is still very much in development, but I'm working really hard on kind of getting this up to speed as much as the chainsig script repo and kind of testing it and everything. But basically, this repo basically demonstrates one of the coolest things, which is that we can sign from other wallets basically an unsigned transaction payload, and then we can actually throw it into a near smart contract, verify that signature, and then we can take that unsigned transaction and we can encode it, hash it, and then call the MPC contract and get a signature for a destination chain, which I think is pretty powerful stuff.
Yeah, I mean, a lot of applications that can really come out of that. So in this setup,
I didn't end up using my video, Joe.
no, this was awesome.
Yeah, but I do want to say that this workshop video here, it's like a tight 23-minute video, and it goes through, at least for the chainsig script example, I mean, it goes through everything. So if you want a walkthrough of that code again and what this repo is capable of, then you can check out the workshop video. It's on the repo itself.
Awesome. So from a hackathon standpoint, anyone can come in, fork these repos, and start building on top of that, right?
Yeah, I think like these repos are probably not, they're forkable, but it's probably better to just kind of use them as basically, they're kind of like kitchen sink examples. So you're going to want to basically kind of come in here. And for example, like you're going to want to just go into the near contract for the cross contract call. So you need to know two things, right? Like, how do I make a cross? Like, how do I have some logic? Like, how do I take in, for example, if you're doing EVM stuff, maybe you're taking in the RLP encoded EVM transaction. How do I figure out whether they're calling a particular method? And then you need to call the MPC contract. So typically, if you're building on chain signatures, I'll go over the three key ingredients that you need to master basically to build on chain signatures. Number one is, how do you derive your accounts, right? Like how do you create these accounts that the user is going to use? And I mentioned that before. It's in kdf.ts. So basically, there's a helper function here down at the bottom. It's called generate address. And you can see calls to generate address and how to create those derived accounts for different chains. So that's step one. Master how to create derived accounts and just understanding that they're always coming from the calling near account ID, whether that is an external account, like just a near client, or whether it's an actual near smart contract. It's the caller to the MPC contract plus the path. The second thing to master is calling the sign method. right? And how to create the different payloads and different transactions that you're going to want to construct to call the sign method. Now, building transactions for different chains can be kind of tedious, but as you can see here, there's like 5 different chains with examples on how to build transactions, including, especially if you're building some EVM stuff, the Ethereum file in the chainsig script basically has everything you'd need to create transactions for an EVM chain. You can deploy, like deploying contracts. The base transaction here deploys the contract. The data is here in the bytes. Calling contracts, so making a contract call to an EVM chain. So it's all here in Ethereum.ts. So that's the second thing you need to master, is how to construct your signature for your destination chain and your destination like derived account, and then how to call that sign method. Now, the third thing is just something that's kind of near specific. If you're building that near smart contract as your application logic, how do you make those cross contract calls, right? And that was, again, that's under the near contracts here. And you can see just down at the bottom, here's how we call basically an external account. And we basically call from one smart contract to another. We call the chain signatures contract. And with those 3 ingredients, derived accounts, calling the sign method of the MPC contract, and constructing your destination chain transaction hashes, and then basically doing those cross contract calls inside your own near smart contract. That's all you need to. That's all you need to know.
Awesome. Yeah. No. I mean, really great opportunity to get involved in this. I think it's great. I'm going to share here too. There's a Telegram group that is specifically geared towards chain abstraction that people can jump into, ask questions. Also, the Near Dev Telegram group, you can always ask questions there as well. But this is something that, while it's new, I think, like you said, there is just a lot of possibilities. It's here, it's working, and so people should absolutely check it out. And in Redacted Hackathon, you can stack bounties, so you can do something with chain abstraction and tie it into something else and go for multiple bounties. So it's worth a shot checking out.
Yeah, I do want to mention the proximity bounties once more. Hacking on DeFi Bitcoin using chain abstraction, so combining near with at least one other blockchain, and always looking for innovative use cases. So we mentioned a few different ways to kind of set this up. You can obviously have near application logic controlling derived accounts, or you can fund derived accounts from other chains, and then have the near smart contract, credit some synthetic token or something if you're doing DeFi. You can work with meta transactions to cover those near gas costs, or you can work with kind of your own relayer setup on the back end. And then the last thing would basically be this user experience stuff with the trade signatures example repo I was showing. I mean, it may not be kind of fully cleaned up and ready for prime time, but all the logic is still there. Like we're still signing unsigned transaction payloads for EVM, for example, with a Bitcoin wallet, and then we're basically parsing that and figuring out that the owner, we're verifying the owner inside a near contract, so we're verifying the ownership there. And then we're using the Omni library to encode, hash those transactions, and then call the MPC contract with a cross contract call and get the signature. So there's a lot going on there, and there's a lot you can just kind of beg, borrow, and steal from those repos, and totally, that's what our role is here. Is like our role is here to just create these example repos, create this base code, and to educate and stuff. So feel free to kind of grab those code snippets. Like I said, it's just a kitchen sink. Just grab those pieces of code and just go nuts and make something really, really cool for the Redacted Hackathon.
Yeah, awesome. Yeah, no, this was great, Matt. I really appreciate your time.
Apologies for no live examples.
That's okay.
Like I know the chain signatures team is they're working very, very hard on uptime right now, and they've just been working tirelessly on it. And I know that I know that we're very, very close to just extremely robust like protocol and uptime and speeds and cost efficiency as well for these signatures. So
Sure.
what I'm really excited about is that you know, I think the chain signatures team is building like kind of the right solution for the future here for multi-chain protocols, and I think that it's going to be fast, cost effective. I think the user experience is going to be excellent. It's already, if you're hacking in the hackathon and you're using the chain signatures, you know, it's already kind of magic.
Right.
So it feels cool every time. Every time I use it, it feels really cool
Yeah.
to be able to, you know, to call a contract, have that, you know, have that signature generated, return to the client, broadcast that transaction, and see it on Explorer. It just feels so cool. There's a few other videos that I'll share in the Telegram channels and stuff like that, where I'm doing this kind of, you know, sign with a Bitcoin wallet, execute on Ethereum kind of stuff. There's a few other videos I'll share as well.
Awesome. That's great. And again, people can always pop into any of the different support channels, ask questions. Near DevHub and Proximity is here to help support you in your building. Well, thank you, Matt. Again, really appreciate your time, and we look forward to seeing you again soon.
Yeah, I'm excited to see what people hack on the hackathon. Thanks again for the time, Joe.
Awesome. Thank you. Take care, Matt.
Take care.
All right. That was great. Again, if you haven't signed up for the hackathon already, definitely go check it out. There are hundreds of thousands of prizes at this point. There are tons of different bounties. There's something for everybody. So it's a great opportunity to kind of just dive in. Even if you're not a near developer, it's a great opportunity to kind of jump in and see what's capable here on near, as well as, again, some of these great different both AI chain signatures and just standard building on an L1 is all available to you. This was a special bonus episode. We still have DevHub Live tomorrow at our normal time, 4 p.m. UTC. So we will be back with another redacted workshop, this time with Aurora. It's building on top of an EVM here on Near. So there's a lot of great stuff still happening. So we will see you tomorrow at 4 p.m. UTC for the next workshop. Until then, take care.